How can a turbocharger make a small engine produce significantly more power without increasing its size? And even more surprisingly, how can it achieve that using energy that would otherwise be wasted? Modern turbocharged engines can often produce power levels that were once possible only with much larger engines. To understand how that's possible, we first need to understand what actually limits an engine's power. Inside an internal combustion engine, fuel cannot burn without oxygen. The more oxygen available inside the cylinder, the more fuel can be burned during combustion. And the more fuel that burns efficiently, the more power the engine can produce. The problem is that a naturally aspirated engine relies mainly on atmospheric pressure and the downward movement of the piston to draw air into the cylinders. Because of this, the amount of air entering the engine is limited. In fact, under normal conditions, atmospheric pressure at sea level is only about 101 kilopascals, or 14.7 pounds per square inch. This naturally limits the amount of oxygen available for combustion. To increase power, we need a way to force additional air into the cylinders. And that's exactly what a turbocharger does. By compressing the intake air before it enters the engine, a turbocharger allows significantly more oxygen to fit inside the same cylinder volume. This enables the engine to burn more fuel and generate more power without increasing engine displacement. At its core, a turbocharger consists of two main sections: the turbine section and the compressor section. These two sections are connected by a common shaft that rotates as a single unit. Although they are housed separately, whatever happens on one side directly affects the other. The turbine is installed in the engine's exhaust stream, while the compressor is connected to the intake system. In modern passenger vehicles, the shaft can spin at speeds exceeding 150,000 revolutions per minute. And in some high-performance applications, turbochargers can exceed 200,000 revolutions per minute. For comparison, that's several times faster than the engine itself. This extremely high rotational speed allows a relatively small turbocharger to move a surprisingly large amount of air into the engine. Inside the compressor housing is a rapidly spinning wheel called the compressor impeller. Its blades are carefully designed to accelerate incoming air at very high speed. As the impeller rotates, it draws air in through the center and throws it outward toward the edge of the wheel. During this process, the air gains a large amount of kinetic energy. The air then passes through specially shaped passages in the compressor housing, where much of this velocity is converted into pressure. As a result, compressed air exits the compressor and flows towards the engine. Because this air is under higher pressure, a greater mass of air can be packed into the cylinders during each intake stroke. And since air contains oxygen, more oxygen becomes available for combustion. This allows the engine to burn more fuel and produce more power than would be possible under normal atmospheric conditions. In many road cars, turbochargers commonly operate at boost pressures ranging from about 5 to 20 pounds per square inch above atmospheric pressure, depending on the engine and application. But what spins the compressor? The compressor cannot create boost unless it is spinning at extremely high speed. In fact, many turbochargers rotate well above 100,000 revolutions per minute. Providing that much rotational energy directly from the engine would reduce efficiency. So where does this energy come from? The answer lies in the engine's exhaust gases. This is where the turbine section comes into play. Every time combustion occurs inside a cylinder, hot exhaust gases are produced. These gases leave the engine at temperatures that can exceed 800 degrees Celsius, and in some high-performance gasoline engines, exhaust temperatures may exceed 1,000 degrees Celsius under heavy load. Along with heat, the exhaust gases also carry substantial pressure and velocity. Normally, most of this energy would simply exit through the tailpipe and be lost to the atmosphere. A turbocharger captures part of this otherwise wasted energy. The exhaust gases are directed through the turbine housing, where they flow across specially shaped turbine blades. As the gases expand through the turbine, they transfer energy to the turbine wheel and cause it to spin. The turbine wheel is connected directly to the compressor impeller through a common shaft, so when the turbine spins, the compressor spins as well. This allows energy from the exhaust stream to be converted into compressed intake air, creating the boost that increases engine performance. The complete process is actually quite simple. The engine burns fuel and produces hot exhaust gases. The exhaust gases flow through the turbine and make it spin. The turbine spins a common shaft. The shaft spins the compressor. The compressor forces more air into the engine. The engine can now burn more fuel during each combustion cycle, and as a result, it produces more power. In short, a turbocharger converts energy from the exhaust stream into useful intake pressure. This process is often called forced induction because air is being forced into the engine rather than being drawn in naturally. Depending on the amount of boost pressure, a turbocharged engine can often produce 30 to 50% more power than a naturally aspirated engine of similar size. There is one important problem. Whenever air is compressed, its temperature increases. In some turbocharged engines, the air leaving the compressor can exceed 150 degrees Celsius. And that's not ideal. Hot air expands and becomes less dense, which means fewer oxygen molecules can fit into the same volume of air. As a result, some of the benefit gained from compression is lost. To solve this problem, the compressed air is passed through an intercooler before entering the engine. An intercooler is essentially a heat exchanger that works much like a radiator. As hot compressed air passes through it, heat is removed from the airflow. The cooler air becomes denser. Denser air contains more oxygen molecules, and more oxygen allows the engine to burn fuel more efficiently and produce more power. An additional benefit is that cooler intake air helps reduce the risk of engine knocking, which is especially important in high-performance gasoline engines. One common characteristic of turbocharged engines is turbo lag. The turbine can only generate boost when enough exhaust energy reaches it. At low engine speed, exhaust flow and exhaust pressure are relatively low. As a result, the turbine spins more slowly and produces little boost. When the driver suddenly presses the accelerator, the engine needs a short amount of time to generate enough exhaust energy to accelerate the turbocharger. Remember that the turbocharger assembly can spin at well over 100,000 revolutions per minute, but it cannot reach those speeds instantly. This brief delay between pressing the accelerator and receiving full boost is known as turbo lag. Modern technologies such as twin-scroll turbochargers, variable geometry turbines, and electric assist systems are often used to reduce turbo lag and improve responsiveness. A turbocharger is essentially an energy recovery device. Instead of allowing exhaust energy to leave the engine unused, it captures part of that energy and puts it to work. The exhaust gases spin a turbine. The turbine drives a compressor. The compressor forces additional air into the engine. More air means more oxygen. More oxygen allows more fuel to be burned, and more fuel means more power.